my name is Qingzhao Zhang, and it's my pleasure to present this paper on data fabrication in collaborative perception, attacks, and countermeasures. So we start from some background information. The perception is a very important component in autonomous driving. However, single vehicle sensor has capability limitations, like they cannot see through the obstacles and they can be less accurate at longer distances. So that's why the collaborative perception is proposed. It's aimed to address the limitation by letting vehicles share data to each other so that they can do the perception jointly and potentially they can make the perception results stronger. So for instance, in the figure below, there's one ego vehicle trying to turn left, and he cannot directly see the vehicle coming from left because of the occlusion. But other vehicles can help to confirm the existence of that vehicle and send some notification message to the ego vehicle so that this communication will make this scenario much safer. And know that there are different categories of collaborative perception. And in this work, we focus on the LiDAR sensor, and which is the 3D laser sensor, and also the V2V setting. The messages are shared among the vehicles. And this is the normal workflow of collaborative perception. I would say the state-of-the-art collaborative perception. All the vehicles in the system do the same perception pipeline for each LiDAR cycle. They first pre-process the LiDAR raw data into some intermediate data like feature maps and share the feature maps to each other. So later, each vehicle can collect all the feature maps from themselves or other vehicles and merge them. And then finally, they can use another neural network to post-process the merged feature map into the final detection results. I know that there's one prior work that quite straightforwardly apply the AI adversarial attack on such a system. So the attacker joins the system and work as a participant, and he aims to use some crafted malicious data to inject as many as false in the final perception results on the victim vehicle. So briefly speaking, the attacker controls that malicious data that is sent to the victim vehicle. So I will use the same threat model in our work. And I want to first summarize what we did in this project, what we did for this collaborative perception security. So we first designed a new attack, which is, we think is more realistic and more stealthy than the prior work. And we'll explain why this is really important. So this attack can spoof or remove objects at a selected location in the final result of collaborative perception. And we also think about the anomaly detection methods. So this leverage the collaboration of multiple vehicles trying to mitigate such an attack, such a new attack. And we emphasize that our experiments will cover both simulation and real-world scenes. So we are trying our best to make our attack and mitigation reproducible in the real world. Okay, so the very first question is why we think the AI adversarial attack in the prior work is not reproducible. So for a very standard white-box AI adversarial attack, to optimize this malicious data, the attacker needs to know, of course, the model parameters and also all the input data. For example, in this case, it's all the feature maps that are going to be merged later in the fusion algorithm. However, in fact, the attacker cannot have all that feature maps in the real world because data transmission needs time, and there's certain events must be happening in a certain orders. So we'll look at the figure for more details. So to attack the perception result generated at this moment, say in the current frame, the attacker needs to deliver the malicious data, which is the malicious feature map, before the victim do the fusion algorithms, which means the malicious data is already generated at this moment. However, the victim vehicle's feature map, which is a necessary data for optimizing the malicious feature map, is only delivered to the attacker way after this deadline, at this moment. So that means the prior attack workflow just cannot happen because of the order is wrong. But it doesn't mean the system is free of attacks. So our new attack will leverage the key idea that the attacker can prepare the attack using some dated feature map, some old data in one frame ago, for instance, to earn some time for generating the malicious data. And we can look at this new workflow. So the difference is that we are now looking at two different frames. The attack impact happens at frame I, while the attacker does the optimization in frame I-1. So the attacker first pre-computes a malicious perturbation based on available data in frame I-1. And later in frame I, the attacker can directly apply that pre-computed malicious perturbation to the latest feature map. And of course, we need some compensation to compensate the time difference between these two frames, which is basically estimating the motion of the objects and slightly tune the location to apply the perturbation. So in this way, the attacker has a budget about 1 LiDAR cycle time to compute this optimization problem. But however, 1 cycle time for LiDAR system is usually 100 milliseconds, which is still a very short time and it's still challenging for the white box reversal attacks. So to address this, we can further do another improvement. We can use the optimization results from the last frame to initialize that perturbation in the new frames optimization. So that's like the optimization is not connected across different frames. So even though the attacker only can do one very weak one-step optimization in one frame, but over multiple frames, the optimization gets stronger and stronger. So all these improvements makes the computation power possible in the in-vehicle devices. So besides that temporal constraints we just mentioned about, we also emphasize the stealthiness of the attack. So we designed the targeted attack, which means the attack impact, either spoofing or removing the object from the perception, will only happen in a certain region specified by the attacker. So the figure below shows the difference between the left-hand side, the untargeted attack, and the right-hand side or attack. So in the untargeted attack, it incurs lots of false detections, and it's seemingly just randomly spoofed. And while that makes it quite obvious that something goes wrong. But in our attack, we only spoof the fake detection in one chosen place. So we argue that it is stronger adversary because the attack is more controllable, and also it's harder for the anomaly detection to know, okay, there's an attack happening. And to achieve this, we designed a loss function shown in the equation. So to spoof an object, for instance, the loss function just tries to maximize the box overlap with the target region, which is provided by the attacker, and also increase the confidence score of the fake detection. And we also think about the mitigation methods. So a key idea here is that the attack perception results usually have conflicts with the knowledge of benign vehicles. So we first like all the vehicles to share some knowledge about this space, so which is the occupancy map. So the occupancy map, like the figure in different colors, it's a 2D map and labels the regions which is occupied by objects, free of space, or unknown. It's like occluded regions. So in this way, later each vehicle can collect all the occupancy maps from other vehicles and try to spot any inconsistencies among them. So for instance, if I saw one object that is on the free space reported by many other vehicles, it's quite a warning that that may be a spoofing vehicle. So one short conclusion for this is that as long as the attack is launched on a region visible to at least one benign vehicle, the attack is likely to be detected. And if there are multiple vehicles can see that region, a major devoting can help to identify the attacker. For evaluation, we first evaluate our attack and mitigation on simulation dataset, OPV2V, including 300 different attack scenarios. So we can show that both spoofing and removing attack can achieve 90% success rate, and anomaly detection can identify 80% of the attacks. Note that we also designed lots of other attacks aiming on other types of collaborative perception systems, like some of them share the raw data, some of them share the processed bounding boxes. And also we have a very long list of analysis, like showing how severe this vulnerability is in different driving scenarios or under different benign faults in the real world. So all these detailed results can be found in our paper later. Okay, so for the real world experiment, we leverage MCD testbed in University of Michigan. So they have vehicles that are all equipped with a full set of sensors, and they have a mock city involving different road conditions. And this is one example scenario we crafted. So here, there are 3 different vehicles. They are connected, and the victim vehicle is trying to do a unprotected right turn. So our methodology here is that we first collect all the data, all the sensor data and network traces in the real world, and run the autonomous driving algorithms in the simulator, like replay all the data. So that's the best effort we can do to like reproduce this in the real world. So in this figure, we can see in the attack, the attacker spoof a vehicle coming from left, so that the victim vehicle is blocked from turning right, because there's always another vehicle occupying the lane. So that caused a denial of service, which is the final attack impact. So some taking away conclusions. Reliability of attacks on autonomous driving or cyber physical systems is greatly affected by temporal and spatial constraints. So we argue that that's the key to make like AI attacks realistic in the real world. And it's a very severe vulnerability for vehicles to depend critical perception algorithms on untrusted data. So that's a very fundamental problem right now. So future effort on improving the security and reliability of collaborative perception is needed. So finally, we have open source artifact online, and I want to advertise myself again. I'm on the job market this year, and I welcome any question. Thank you so much.